Today I'm going to talk about optical circuit switches for AI data centers. That's what we do at iPronics. I think this is something that you all know. Don't need to explain too much here, but just to kind of set the context. As you know, the density of AI compute is increasing in terms of GPU dies per package, and also how many GPUs you can fit in a rack, and then how many racks you connect, right? So NVIDIA is executing phenomenally well with release of GPU every year, new generation of GPUs every year, and the density is increasing phenomenally. So all this networking for the GPUs, as you can see, there's stringent requirements on it, right? There's the networking within a domain for computation of these AI training workloads, that is scale up, and then connecting all these domains together, that's scale out. So lots of requirements on networking. And one of the biggest challenges as you scale the AI clusters is reliability. Any sort of errors in the network, either it's coming from GPUs or from the network itself, can drastically affect your training or inference performance, right? And then there's also needs for reconfiguring these AI clusters because every training model requires a certain type of traffic pattern. So you should be able to reconfigure this AI cluster on the fly. And so all of these requirements are there, and all of these requirements are being put on the AI data centers in a very power limited and a space limited conditions, right? So we don't have as much power to power all of these things up, and neither do we have as much space. So any solution that's going to solve these problems should be power efficient and space efficient. So how do we solve these requirements, right? So any solution that's being developed needs to be cost effective and mass producible, right? So if it's not cost effective and mass producible, it cannot get used in AI clusters. And because of the power demands, low power consumption is also quite important. And reliability, of course, anytime there is a failure, it's going to affect the workload, so it needs to be reliable. And reconfiguration should be fast, not only just the ability to reconfigure, but it needs to be fast. And we solve all of those things using standard silicon photonics. That's how we do it. So what do we exactly do? We actually build gain-controlled optical circuit switches that are low power and high performance. We have built a bunch of IP in iPronics, which we use to kind of build these optical circuit switches. As you can see on the slide, there's the Photonic IC, and then we also build all the necessary software and control electronics that need to go along with the PIC and the system itself. So this is an optical circuit switch that is built using standard silicon photonics technology, which consumes very low power, and it also has amplification. So any loss you may encounter using the silicon photonics waveguides, you can actually compensate. So looking at what we have done so far and what we will be doing in the future, at OFC this year, we demonstrated our optical networking engine 32, which has 32 ports, and that is sampling to customers since Q2 of this year. We have a 64 port version, 128 and 256 port version on our roadmap. The system itself, as you can see, has the silicon photonics chip. It has all the control electronics. It has the optical amplifiers, and it's a 1U box for the 32 by 32. It's quite the feat. The PIC itself has over 2,000 programmable unit cells, we call them, which are basically the Alexander interferometers. And then we have about over 4,000 actuators, in total around 10,000 components on the optical subassembly. So quite the fascinating device, and it's sampling to customers, and we have a roadmap to double it next year and then the years onwards. So another interesting thing about our device is it needs to work with existing optical devices out there, whether it's pluggable transceivers or near packaged optics or optical interposers or even co-packaged optics. So you can actually take the fiber from all of these optical devices and connect them to the optical circuit switch that we're building, and you can achieve the optical networking goals that you have, right? So using the optical circuit switch, you can actually reduce your link cost, because you're actually removing a couple of transceivers and potentially an electronic switch in the middle, right? And we also have all the telemetry that is needed, as well as the link gain. So that helps with deploying this switch in more places. And we also have under a millisecond reconfiguration time. So that's also helpful for AI workloads. One of the concerns people would have when you are looking at silicon photonics based optical circuit switches and optical amplification is the impact on the bit error rate. And so this is measured bit error rate on our 132 device across the O band, the full spectrum. And as you can see, it's pretty flat, and sometimes the degradation is less than 1 decade. So it is in the range where it's not going to affect the link operation. So in summary, we've been using silicon photonics to build these devices, which allows us to build an optical circuit switch that is cost effective. We believe it will be lowest cost per port. The ability to mass produce these devices and have high reliability. Other optical circuit switches may use movable parts. There's no movable parts in this one. So that's going to help with reliability. And because we have optical amplifiers, we can bring the optical loss to zero. And we also have system telemetry and compact devices, about 1U rack for the 32 port. And we can try to keep it the same for 64, depending on the connector and so on. And of course, fast reconfiguration. So all of these aspects will help make this optical circuit switch very suitable for AI data centers. With that, I will end my presentation and hope this was useful.